So I want to start to thank organizers for organizing this great conference. So and for the opportunity to speak. So I'm gonna speak about the topic in non-Hermitian random matrix theory. So we have a random matrix like this gonna converge to some to a W-star probability space. Sorry. So it has it's a finite from algebra with a phase for normal tracer state. We're gonna look at the eigenvalue distributions of matrices, in particular for non-Hermitian random matrices. So there's a generalization of this in the context of operator algebra. You can make sense of this eigenvalue distribution for any operator in this finite from algebra, meaning like you look at the trace of log of this operator, which is the logarithmic determinant, Fourier-Scattering determinant. Then Brown showed like this actually is a right analog of in classical potential theory. He proved like this actually give you a subharmonic function. Then we take a distributional Laplace function. This give you a probability measure. So this is called a Brown measure. So this, because of machinery of free Weierstrass's free probability, one can expect like the if you look at the Brown measure of limiting operators, this should give you prediction of limiting eigenvalue distributions for non-normal random matrices. So main question like in this field, maybe one of the main questions probably is like to prove the convergence in terms of eigenvalue distribution or Brown measure. So Weierstrass's convergence says like you have this convergence in moments, mixed moments, but this convergence in mixed moments does not imply like convergence in Brown measure in general. Yeah, so, but still, like this is a very powerful framework. Like one can expect, like at least for many cases, it is known like the Brown measure of limiting operator give you limiting distribution. So there are a couple of questions. Like question one maybe is like if we can calculate the Brown measure of some interesting operators from free probability. The other thing is that you can prove a convergence. This actually is helpful sometimes. Like if you know some properties of Brown measure, it gives us some information how to prove convergence. Okay, so just to give you some quick review about we studied the non-Hermitian random matrix model. IID random matrix model, you look at the MIN square matrix. Entries are independently identity distributed of a given random variable, given distribution. So you can think like this is Gaussian. Then it's known like for under very weak assumption, like the eigenvalue distribution converges to the uniform measure on the unit disk. So in this case, is a Brown measure of Weierstrass's circular operator. So circular operator is complex Gaussian in free probability. Because one can write, for instance, if these entries are Gaussian, you can write it as two copies of GUE, like so give you analog of circuit complex Gaussian. The model in this talk I'm going to look at is related to the single ring model. So you look at this model U sigma V star. So this UV they are sampled from higher random unitary matrices, and this sigma n they are positive diagonal matrices. So you can think that this give you a randomized singular value decomposition of a matrix. So this model is related to operator like in free probability is related. The limit operator is R-DAG operator in free probability. So Hargrave-Larsen calculated the Brown measure of this is supported in a certain single ring and is constant around this family of circles. And actual convergence was done like by these people, like so it's known as a single ring model, single ring on law. Okay, so what is R-DAG operator? So these are family of non-Hermitian or non-normal operators introduced by Nita Specher. They generalize higher unitary operators and circular operators. So in this case, like this random matrix model, you can think that this converges to higher unitary operator times another operator link another operator. But this is you can take a conjugation by another higher unitary operator, so that this converges to these product operators. One is high unitary, the other one is a positive operator. So this is general form of R-DAG operator. In particular, for circular operator, this is this polar decomposition. This is the absolute value of a semicircular operator. So the name at least goes R-DAG operator because actually only non-Venetian free cumulants are given by this model. Only like these kind of free cumulants are non-zero. But this is not important in this talk. Okay, so I want to give you some comparison about some results. Like first of all, we can think that at least in a limit level, the R-DAG operator is a generalization of circular operator. So there's a well studied like the model is deformed Geneva or IID random matrix model. We say is that you look at IID random matrix model, which will converge to circular operator. On top of that, you add additional operator AN. This AN will converge in star moments to X. And it is known like the Brown measure or eigenvalue distribution of the summation will converge to the Brown measure of this. And one can actually calculate the support of this Brown measure and give some kind of explicit formula for this density function. It is absolutely continuous for any x, absolutely continuous for any x, and one can identify some open set. Here, this is example. On this open set, we can give some formula, trackable formula to express the density formula.
Sorry, AN is self-adjoint or?
AN is a deterministic matrix converges to some operator.
But not you don't need that it is self-adjoint?
Yeah, here in this sampling, I choose a self-joint, but you can choose any operator, not necessarily self-joint. Yes. But the support is known that is closure of this open set. So which means that the trace of the negative L2, so negative L2 known that is bigger than 1.
Okay. This is a general statement about Brown measures or just for this model?
This is a general statement of this Brown measure. Like the support is exactly equal to closure of this open set.
For every x in any.
For any x, right? Not necessarily normal, right? So for the normal case, actually, it is known like from work of Bordenov, Capitan, and Chafin 10 years ago, and later we clarify this for generality. Okay, so the model we look at is like the perturbation of this single ring random matrix model plus additional AN. This AN converges to X in star moments. gonna report to you like the Brown measure of this addition x bar t, and then convergence of that under some assumptions and outliers. So these are some simulations. So this single ring give you this support. If you perturb that, one thing I just want to point out, like potentially there's a disk. This disk could be collapsed to a single point, or there's no like no disk anymore. But outside, like we look like this. So this outside domain actually is is exactly same as the outer boundary you see when you look at deformed IID random matrix. So meaning that if I only care about all this outer boundary, I can replace this model by IID random matrix. I can produce the same outer boundary. But for this inner boundary, that this is a circle. This is spatial for this R diagonal operator. So we prove like it's actually we can identify an open set, which I denote this by omega. So the picture looks like this. Like you can, it's characterized by two conditions. Like one is that this product is greater than 1, the other one is this product is greater than 1. They are very similar identities. If I look at this second inequality, this actually this gives us this boundary. If you look at this condition, that gives us the outer boundary, right? So as I mentioned, like no matter what observation you work on, like you can always see like this inner disk potentially. Okay, so this is special about this. So we can actually also give a kind of a density formula in this open set. This density formula can be given by subordination functions in free probability. Okay. So first is about the convergence. We show like under some assumptions that the eigenvalue distribution of this model converges to the limiting the Brown measure of limiting operators, canonical operators. So in the convergence, there are usually two steps following like the method of Gerger, and now is a standard method to improve convergence of eigenvalue distribution for non-Hermitian random matrices. So first is you look at the absolute value of this matrix, or you look at the Hermitian reduction of that. So this will converge to a measure. Like this measure, you will see that is this measure. Like is the spectral measure of family of operators, primarily charged by this Z. The other thing is pretty technical thing is to prove that this log is uniformly integrable. So it's a question about distribution of smallest singular values of random matrix. So to prove this, actually we didn't do much for this second part. We just use the seminar work of Ludus and Vosini, where they obtain like the very nice result about smallest single value distribution for this model. So what's the intuition like to see is that when you look at this matrix, like you look at this Hermitian reduction, then you try transform like the proof of first step is about the Hermitian reduction. You put this y minus z star, like this becomes like a Hermitian matrix. And actually this gives you information of singular values of y minus z, or the symmetrization of the singular values. So to see that why like this is related to summation of two freely independent operators, you can look at this decomposition. These UV, they are not full higher unitary matrices, but still like give you enough symmetry so that the limit operators of these two, they are freely independent. So like this, actually, to study the distribution of this is about the study of free convolution of symmetric measures or convergence of this model. Okay? So in the operator value or operator level, you look at the summation of a higher unitary operator UH plus X. There's a trick like about this symmetrization. If you take the absolute value of this, UH plus X minus Z, look at the spectrum measure of that, then symmetrize that. After you do this symmetrization, just like here, this is the limit operator, limited distribution of this side. This will be equal to the free convolution of two symmetric probability measures. So one is about the symmetrization of this H, the other one is the symmetrization of this X minus Z. So this actually is the hint like what is needed to prove like this convergence. Let's finish the first step of the convergence. So next I want to discuss like the outliers. So which means that now like my perturbation has two pieces, AN prime and AN double prime. So this AN prime is very well behaved. So meaning that if you look at only AN prime, AN double prime is equal to 0, then like this limit should not have any eigenvalues, has no eigenvalues outside the support. But what this AN double prime does is that you create some finite rank matrix, and this finite rank matrix has some eigenvalues. They are not in the support of the broad measure, not in the limit measure. So as you can see, so here these outliers, they are denoted by red. So if these are eigenvalues for AN double prime, so maybe it's pretty small, but this, for example, this is here I have an eigenvalue for AN double prime, which is red, and I have blue one is the outlier for this summation, and you can see that they are pretty close to each other. And also here, if you have an outlier for AN double prime, you have an outlier for the summation. The other phenomenon is that if you look at the inner ring, I have some outliers for AN double prime, but when you look at the summation, there's no outlier anymore. That these outliers will be killed in this disk. Okay, so this is like actually the result we prove that for this for outliers for this deformed model. So I could point out that this generalized, not generalized, but similar results holds if you look at this perturbation by IID random matrix model. Then in that case, there's no inner disk anymore. And then like the outliers outside the spectrum are very like stable in this case. Okay? If you look at the well-behaved perturbation. And So what's the ingredients? First, like if you look at if I pick any compact set outside the spectrum, if the perturbation is well conditioned, which means that the smallest singular value of n prime minus z is positive. So this is invertible actually. Then we show like the improbability one, like this perturbed version has no outlier like there. Okay, so this compared with perturbation of IID model. So this was studied by Tao, and then so Tao studied like the finite rank perturbation, meaning like this an prime is equal to 0. You only look at the finite rank perturbation, and later Bodinov or Capitan they generalize this to 4-rank perturbation, meaning that they look at this similar model, but an prime will converge to some non-trivial operator. So this also generalized. Well, the finite rank version for single ring model was studied by Benaych-Georges, and I think the other also is Guionnet, 2015. So here we look at 4-rank perturbation. Okay, so just recall like this the support of Brown measure is characterized by 2 conditions. So naturally it has 2 domains. One is that this theta in, so which is this disk. The other one is the outer domain. So this condition, you can see that this condition give you a disk, but this give you some curve like which is pretty wild for this one, the boundary condition. Here we have to make some assumptions. Maybe first one probably is pretty strong assumption. Like we have to assume that the support of this Brown measure is equal to the spectrum of this, which is in general is not true. But for cases like for few cases like which are like in particular, for instance, that if T is invertible, then this is true. This assumption, like we need this assumption because we only have information about the Brown measure, but we want to use techniques of this Hermitian reduction. Actually, Hermitian reduction method essentially you study these singular values, which is about this spectrum. So we need this assumption to make sure like we can transform like information about the Brown measure to the spectrum. So a question is that I'm not sure that how general this could be true, like if T is R-like operator. If T is a circular operator, then under some assumptions that this is true. Okay. So what's the theorem? We look at this perturbation. An has 2 pieces, An prime and An double prime. An double prime is finite rank matrix, which is a fixed number. But this N dimension of matrix grows, but this rank of An double prime is fixed. Okay? Assume that this condition holds. This basically says that An prime will not create An prime itself will not create outlier. Then like we can show like this the outlier on the outside. If you look at some compact set in the outer domain. So I have two domains. One is inner disk, the other one is outer domain. Then that in the outer domain, that the outer layers they are stable, meaning that asymptotically, like the location of outer layer for A and double prime is same as outer layer of the summation of the perturbation. Okay. So we have not studied right now. There are some questions, further questions that we have not studied about the fluctuations of stable outer layers and unstable outer layers, which are also interesting questions. So we not fully generalize, but compare like our model with our other model, like the four-rank deformed ID model. We try to generalize this to a four-rank perturbation of single-line random matrix model. Okay. So this is the result, as I mentioned. Like for outer layers in the outer domain, this will remain, and asymptotically the location of the eigenvalue for A and double prime will be the same as the location of outer layer for this summation. And in the disk, there's no outer layer. The outer layer will disappear. Okay. So this comes to like the second part of this outer layer result is that for this well-behaved perturbation in the disk, there's no outer layer anymore. So these two dots are eigenvalues for A and double prime. So when you look at this full-rank perturbation, they will have no contribution for outer layer. Okay. In the remaining part, I want to give you some idea of the proof. The proof actually follows from like the results or proofs for full-rank IID random matrix model, plus additional ingredients from free probability about this Brown measure. And also the other difference is that because we work on different random matrix models, that towards usually are different, but the overall the method is that to use this Sylvester's identity. So this AM prime is well behaved, so it will not create an eigenvalue. So like this matrix perturbation by AM prime itself is invertible. And we want to compare this with resolvent of AM prime. So if you want to look at the outer layer, so you want to look at the zero of the characteristic polynomial. So this determinant, because like this is, because this is invertible, so you can extract this information. Suppose that this you rewrite this AM double prime as a product of finite rank matrices. So this R is the rank of AM double prime. So this if you use this identity, this transforms like this determinant to a determinant of small rank matrix. Okay, so if you look at the zero of this, because this is non-zero, we can by the result of no outer result, then to determine that location of this zero is eventually to determine the zero of this small rank determinant. So we have this formula. So similarly, like you can write this determinant of AM prime as this product. So because like the AM prime and AM prime is well behaved, so this determinant will be non-zero. So therefore, like to determine to compare zeros of of this perturbation and AM minus Z, essentially you want to compare like these two determinants. So the idea is that to show that these two resolvents are close to each other, that in this in operator norm. So therefore, that these two determinants are almost equal to each other. Like and then Lucius' theorem tells us that the outliers are stable. So we need some version of weak version of strong convergence, like the convergence in norm. So here we actually following like the approach from deformed IID model, but for convergence of in norm, we have to use Weingarten calculus that also like results of Collins-Mayer and Belinsky-Capitan. So I have feeling that probably like because we have many experts in this norm work on strong convergence, probably like this could be a consequence of some known results, but I don't know. I mean like a convergence of in norm of this resolvent. So for non-outlier, that the process is similar, but the behavior is different. Like in this case, these two resolvent they are different, but you can show actually this resolvent goes to zero, because like the definition of two domains they are different. Like this makes these two convergence to be different. I will try to use free probability to give you some intuition at why like these two domains that have different behavior. So first is about Fugler-Skarsgård determinant. So if I look at the Fugler-Skarsgård determinant of the summation for any z that in an outer domain, then this determinant of the summation, so this is the Fugler-Skarsgård determinant of limit operators, is equal to determinant of x minus z. So this gives us a kind of a hint like why like the outliers are stable. On the other hand, if z is in the disk, then the determinant actually is constant. So like this completely different behavior for this determinant. So this actually so this is a consequence of the general result, meaning that if you look at the determinant of two R-diagonal operators, if one R-diagonal operator is very big, the other R-diagonal operator is pretty small, then that one of the R-diagonal will dominate the determinant. Okay. So in particular, like this, we have this result because like when you look at this determinant, you can is equal to essentially same as the determinant of t plus additional R-diagonal operator. Okay. So this the method to prove this to obtain this determinant formula is to upgrade the argument from Hargrave-Schultz. So where they give second proof of parameter of R-diagonal operator. What they look at is implicitly they use the subordination function to look at reduce the question to study that this free convolution of symmetric measure with Bernoulli distribution. What we need to do here is that look at the free convolution of two arbitrarily symmetric measures. Okay, so another explanation is that these two resolvent, if you look at the outside domain, if I only look at the limit operators, that these two resolvent has the same expectation. I will see that in my next class. Okay, so another hint, like to see like the convergence of this goes to zero. Actually, this is we can find a clue like from this condition. Like the condition is this x minus z L2 norm is less than like the inverse L2 norm of t. This like to prove this, the main ingredient to prove like the radius of this product is small, is less than 1. So like we can use Taylor expansion like to get this proof. So a little bit more details that we like to detect that the Brown measure we use Weierstrass's free convolution. So in particular, we look at the free convolution of two symmetric measures in this case. So it's known like there are two pairs of there are pair of subordination functions omega 1, omega 2. This is subordinated with respect to this Cauchy transform. So these functions are pretty useful to study like the boundary values of Cauchy transform that essentially give you information about the spectral measure. Okay. So in our case, like because like the operators are non-normal operators, so we have to, but tools are only available for Hermitian operators. So the standard method is to look at the Hermitian reduction. So here I have little x, little y. I look at the capital X, capital Y. So these are matrix 2 by 2 matrix valued operators. So if x, y are independent, then freely independent, then capital X, capital Y, they are freely independent over 2 by 2 matrices. There's also like the subordination functions. If y is R diagonal, in this case, that this subordination function actually has very spatial form. So we can like this. We basically that here like this I epsilon place here z like you want to detect the information about this z, and this I epsilon is a regularization parameter. So this subordination function will send this to similar form, a matrix of this similar form, but this I epsilon is actually is a value of subordination function when you look at the free convolution of these two symmetric measures. So meaning that to detect the information, we have to study the family of subordination functions. Okay, so more precisely, that we look at the behavior for as epsilon go to 0 for different z's, that the behavior of the limit of this subordination function is different. One region is infinity, the other one is 0. Then like in the domain is finite number. Okay, that makes like that can detect like the support of Brown measure. Okay, so let me stop here.